In this video, we're going to provide a proof that under the Gauss-Markov assumptions, the ordinary least squares estimator is the best linear unbiased estimator. The Gauss-Markov assumptions can be stated as shown here. First of all, the error has expected value 0. Secondly, the errors are independent, so the expected value of ui multiplied by uj is equal to 0 for all values of I not equal to j. Thirdly, the errors have constant variance, so the expected value of ui squared equals a constant for all values of I. And finally, the x variable is not itself a random variable, so if we write the expected value of xi ui, we can take the x outside the expectations operator, and that of course will mean that the x's are uncorrelated with the error terms by definition. For simplicity, we're going to consider the case where there's no intercept. So we have yi equals beta xi plus ui. And we can define the OLS estimator as the sum of xi yi divided by the sum of xi squared. We can think of the OLS estimator as a weighted average of the y's, where we write the sum of ai yi, where the ai's are a set of weights defined as xi divided by the sum of xi squared. We've also shown that under the Gauss-Markov assumptions, OLS is unbiased, so the expected value of beta hat equals beta, and the variance of beta hat is equal to sigma squared u divided by the sum of xi squared. Now let's consider an alternative estimator, beta tilde, which is the sum of gi yi, where gi are a set of weights defined as follows: gi equals ai plus hi, where at least one of the hi's is non-zero. And we're also going to assume that beta tilde is an unbiased estimator, so the expected value of beta tilde equals beta. We can write beta tilde as the sum of gi beta xi plus ui, and multiplying through, that's equal to beta times the sum of gi xi plus the sum of gi ui. Now, since beta tilde is unbiased, the sum of gi xi is equal to 1. Therefore, the sum of ai plus hi xi must be equal to 1, and this in turn implies that the sum of hi xi must be equal to 0, since we've already shown that the sum of ai xi equals 1 because OLS is unbiased. So the variance of beta tilde is equal to the expected value of beta tilde minus its expected value squared, and of course beta tilde is unbiased, so that's equal to the expected value of beta tilde minus the population value of beta squared, and we can write that as the expected value of the sum of gi ui all squared. Next, we substitute for gi to write the variance of beta tilde as being equal to the expected value of the sum of ai plus hi times ui all squared. By standard Gauss-Markov assumptions, the expected value of ui and uj is equal to 0 for all values of I not equal to j, and the expected value of ui squared is equal to a constant, sigma squared u, for all values of I. This means that we can write the variance of beta tilde in the following form. We have the sum of ai plus hi all squared multiplied by sigma squared u. Now, expanding this expression, we can write it as sigma squared u multiplied by the sum of ai squared plus the sum of hi squared plus 2 times the sum of AI HI. Now let's consider this cross product term in more detail. The sum of AI HI can be written as the sum of XI HI divided by the sum of XI squared. But we've already shown that the sum of IHI is equal to 0, and therefore this expression is also equal to 0. Therefore, we can write the variance of beta tilde as being equal to sigma squared u multiplied by the sum of AI squared plus sigma squared u multiplied by the sum of HI squared. Now let's substitute for AI, and we have the sigma squared u multiplied by the sum of xi squared divided by the sum of xi squared all squared. Again, plus sigma squared u multiplied by the sum of hi squared. This in turn is equal to sigma squared u divided by the sum of xi squared, which is just the variance of beta hat, plus sigma squared u multiplied by the sum of hi squared. So therefore the variance of beta tilde is equal to the OLS variance of beta hat plus a positive number, and therefore it has greater variance than the OLS estimator.